So hi friends, in this lecture we will discuss about the head loss due to friction, which has been derived by Darcy Weisbach. So it is like the major loss of an energy uh, when fluid tends to flow in a circular pipes. Right. So the Darcy Weisbach statement. So it is an equation in fluid mechanics named after Henry Darcy and Julius Weisbach. So we call this a Darcy Weisbach equation, which relates the loss of pressure or a head loss due to friction along a given length of a pipe to the velocity of a fluid flow for an incompressible fluid. So we are discussing about incompressible fluid. So it's a liquid. So when a liquid that flows in a pipe for a given length, so there will be some energy loss. So that energy loss we're going to discuss and we're going to find out. So the Darcy Weisbach equation is head loss due to friction. HF is a head loss due to friction, which is equal to 4F LV square by 2GD. F is a coefficient of friction, or called as a friction factor. V is the velocity of an incompressible fluid. L is the length of the pipe. D is the diameter of the pipe, and G is acceleration due to gravity. Generally, it's 9.8 meter per second square. So let's go into the derivation of Darcy Weisbach equation. So how this equation is being derived and based on the assumption. And so step 1, terms and assumption. So consider a uniform horizontal pipe with fixed diameter D and area A, which allows the steady flow of an incompressible fluid. So we have taken a pipe, so its diameter is fixed and length is fixed, which allows a steady flow of an incompressible fluid. So it's a steady flow, so there won't be any change in velocity with respect to time. So we assume that the flow is steady and it's an incompressible. For simply consideration, so we take S1 and S2. This is section 1 and section 2 of a pipe separated by a distance L. So you know that we are actually to follow Euler-Run method. So it's like a controlled volume. Okay. So section 1 and section 2. So here we're going to discuss about the fluid energy losses. At section 1, all points of section 1, the pressure P1 and velocity is V1. At each and every point, the velocity will be V1 and pressure will be P1. At section 2, at all points, the pressure will be P2 and velocity will be V2. There won't be any change with respect to the distance. Okay. So consider the fluid flow as shown in figure. Thus, the pressure at S1 is greater than the pressure at S2. Yes, of course. If there is a change in pressure, probably then the fluid tends to move. If there is no change in pressure, the fluid cannot actually move. Right? So P1 will have a greater pressure compared to P2, so the fluid tends to move towards the forward direction. So when fluid flows, there will be some loss of energy, which might be due to friction that we're going to discuss. So thus we can apply Bernoulli's principle. So when there is a fluid flow, so we know that the basic equation will be Bernoulli's. So Bernoulli's defines energy is in a fluid flow. So pressure energy, kinetic energy, datum energy, which is equal to constant for an ideal fluid. So but for a real fluid, we know it will be having some energy losses. So the Bernoulli's principle, which states that a decrease in pressure or a potential energy of a fluid increases the velocity or speed of the fluid flow. In other words, because for a incompressible fluid, the sum of its potential energy, pressure energy and velocity remains constant. That's why we have already discussed in Bernoulli's equation derivation, where the potential head, the pressure head or kinetic head remains constant throughout the flow for an ideal fluid. So here it states that if there is any decrease in pressure energy or potential energy, then one or other has to increase, right? So the velocity of a fluid tends to increase if there is a decrease in pressure energy. So based on Bernoulli's principle, we have going to derive an expression to find head loss due to friction. So applying Bernoulli's equation, so P1 by rho g, which is a pressure head, V1 square by 2g kinetic head plus Z1, which is for section 1, which is equal to P2 by rho g plus V2 square by 2g plus Z2 for section 2 plus head loss due to friction. There will be some energy loss for a real fluid. Okay, so if it's ideal fluid, so it will be equal to constant, but it's a real fluid, so we'll have some head loss, which is energy loss. So for a horizontal pipe, so there won't be any datum, right? So the reference of a reference plane of the pipe will be same. So Z1 will be equal to Z2. Here diameter is uniform, and we have taken it's an a steady flow, so velocity remains constant. So V1 will be equal to V2. On substituting them, the equation 1 becomes P1 by rho g equals to P2 by rho g plus head loss due to friction. So V1, this terms becomes cancels out, and Z1 will be equal to Z2, so it gets cancels out. So P1 by rho g equal to P2 by rho g plus HF. So on rearranging this, so HF will be equal to P1 minus P2 by rho g. So HF into rho g will be equal to change in pressure energy or a pressure head. So P1 minus P2. So now we need to find what is the frictional forces. So we have a pressure force. So the forces are the pressure force and a frictional force. So pressure force we have found that. So now we're going to find what is the frictional force on a moving fluid in a pipe. To find the frictional force, so we know that on a surface roughness, so each pipe has its own surface roughness. So when a fluid flows on a pipe, there will be some resistance force that we call it as a friction. As due to this friction, there will be a reduction in speed. So the fraud has done an experiment and has found few statement that the fluid friction for a turbulent flow, so because we are discussing for a turbulent flow, so fluid friction for a turbulent flow, the frictional resistance of a turbulent flow is proportional to V power n, where n varies from 1.5 to 2. So this is what actually been discussed in Reynolds experiments also. So where the resistance or the loss due to friction will be directly proportional to velocity in terms of laminar flows, but for turbulent flows, so velocity will be, the friction loss will be directly proportional to V power n, where n varies from 1.75 to 2. Okay, so and also frictional resistance is directly proportional to area of surface contact, so where the fluid actually gets in contact, the surface contact. So right, so based on that, the frictional resistance will be equal to F dash, so which is a frictional resistance per unit wetted area per unit velocity, per unit velocity per unit area. So what will be the frictional resistance? That is denoted by F dash. To find the total frictional resistance, so F dash into wetted area, so perimeter, so 2 pi L into V power n, so we're going to take the maximum value, so V square. So F dash, which is equal to pi d L into V square, so 2R, which is here d, so V square. So this pi d is the perimeter of a circle, so take it as P, and L is the length of the pipe. Right, so this will be the frictional force on a pipe. So now the net force acting on a fluid at section 1 and section 2. So what is the forces that is been acting on a pipe? So section 1 and section 2 we'll have a pressure force, right? So pressure force at section 1 and pressure force at section 2. So pressure will be equal to force by area. So force will be equal to pressure into area. So at section 1, and force will be equal to pressure into area at section 2. So at section 2, what happens? From section 1, the fluid tends to flow. So section 2 is a force which is an opposing force, so we'll have a negative sign. And the frictional force is also opposing force, so you can see from the picture. So from here the fluid tends to flow. So this is due to the pressure force, the fluid tends to move. We'll have an opposing force, which is opposing pressure force, and a force which is due to friction. These are negative, this is opposite force. So negative for pressure force section 2 and negative for friction force, okay, because it is opposing the direction of the fluid flow. Right. So the total force will be P1 A1 minus P2 A2 minus F, which is equal to summation of force. So F will be equal to P1 minus P2 into A. So because diameter remains same, so the area remains same. So P1 minus P2 will be equal to F by A. So already we know P1 minus P2, which is equal to HF into rho G, and F, which is equal to F dash into PL into V square. So we're going to substitute these values in this equation. This will be HF into rho G, which is equal to F dash PL V square by A. So I'm rearranging this. So HF will be equal to F dash PL V square by rho G A square, which comes to the denominator. So already we know that P by A, which is a vector perimeter area. So P is a pi d perimeter, L is a A is the area of the cross-section area of the pipe. So pi by 4 d square. So to simplify this, it gets 4 by d. So instead of P by A, we're going to substitute 4 by d. So this equation becomes 4F LV square by rho GT. So instead of F dash by rho, so we're going to substitute F by D, because the fluid is an incompressible, which means that when external force is applied, there won't be any change in density. So we're going to take this density out. So HF will be equal to 4F LV square by 2 GD. So instead of F dash by rho, we have substituted F by D, where F is the frictional resistance, coefficient of friction, and F dash is the frictional resistance. So this equation becomes HF, which is equal to 4F LV square by 2 GD. It's a Darcy Weisbach equation. So we have derived. So this frictional coefficient, or coefficient of friction, we call it as a friction factor, is being identified based on Reynolds number. So if the Reynolds number is less than 2000, which means if it's a viscous flow, the frictional coefficient will be equal to 16 by RE. If it's greater than 4000 to 10 power 6, so the formula to find the frictional coefficient 0.079 by RE power 1 by 4. So this is how you find out this frictional coefficient, where L is the length of the pipe, V is the velocity, G is acceleration due to gravity, and D is the diameter of the pipe. So hope you guys have got a clear idea how this head loss due to friction is being derived by Darcy. So this is a very important derivation. So thank you guys.